And our first speaker is Pedram Roushan from Google, and he's going to tell us about what the Google folks are up to. The floor is yours.
Yes. Okay, I think I don't need to stay so close to it, so maybe I stay here or something. Right? I think we are good. You can hear me easily. Yeah, I have a couple of confessions to make, and I make them as I speak. Let me get the timers going before the confessions. So I do maybe 30 minutes and plus questions. So I'm about to tell you some of our recent works that we have done. But I have to make a confession that I get really confused about the title of the workshop and its focus on the word entanglement. And I try to maybe give our view of what entanglement means to us. By going over these examples or from our recent published or posted on archive works, I try to explain how our platform works. And basically, it comes down to choosing a model, choosing a spin model, and rather than realizing a ground state as a phase of matter, we would synthesize, we would simulate a quantum states, and then we have the capability to do lots of various measurements, and that's why entanglement particularly doesn't stand out for us. But also, I can show you that we can manipulate states because the control that we have over the system. So instead of giving me my regular introduction that we have nonlinear resonators, they are Josephson junctions, and they are coupled to each other via element called coupler, and then all that kind of a standard thing. I just show you this slide to show that we have big atoms. Essentially, we have every of these spin 1/2. Every of these coded object is a qubit. So I just want to tell you that by training, I'm an experimental physicist, so you don't ask very hard questions from me. But the real true inspiration came at 9:42 when I saw a laundry list of requests. Oh, we want to do this, we want to measure this. Okay, sure. I heard very clearly that, for instance, you want to study toric code model and you want to measure excitation in this model. So I don't need to say much about it. But what I can tell you that, let's say we want to study this model that nicely was introduced this morning. So Kitaev model is where our billion-dollar industry is, well, not billion yet, but okay. 100 million industry is built on by Google, IBM, and all these companies. We are trying to essentially realize and work with the ground state of this model. It was nicely explained, so I don't go very much tell you much about it. It's just a showcase of how it works. Well, what we could do, as I said, you need a pulse sequence, and it was demonstrated in this work, which is a few years old now, that you use a pulse sequence to arrive at the ground state of this model. It was also mentioned this is exactly solvable model. So there is a very clear recipe on how to make the ground state of it. Is a sequence of CNOT gate and Hadamard gates gets you there. So when you get to the ground state of this model, what you could do, you can go and do as much correlation measurements that you like, 2-point correlations, 3-point correlation, any probably a string of any order. I would not go over the detail of this one. This is not the pet project I want to explain to you. But this, for instance, this Kitaev Preskill topological order that has been predicted to exist in this model can be measured as you do all local measurement of entropy over a small group of qubits, and you put it together in this formula, and you can get nicely measure this universal kind of size independent topological entanglement entropy in this model. So that's the capability of measurement manifested in here, but also in the laundry list of requirement that Nandini put together. There was, oh, can we braid them together? Okay, we can braid them together. You can create excitations on demand, and you can move them one around by another one by applying pi pulses or z pulses and whatnot. In this case, you get a global phase. That's a bit silly. You can't do any. You can't extract it out, but you can do some standard textbook tricks, which allows you to read that phase if you wish, and then you can do the S and T matrices that people have been talking about, and that's the braiding of these boring abelian excitations. In this case, there is E and M, and there is a fermionic excitation. You can do exchange, and you can do what's the other one? Mutual. And you can just see if there are 0 and pi. These are abelian particles, and they would just do some boring phase accumulation. They don't change the local wave function. So this is my this is my introduction of what. Yes, sure.
This can be done. Like
2 years old.
Yeah, but you can do X and Y and Z and braid them and so on.
That was the whole point of these 3 slides. And then the next work we did non-abelian. That's what I said, this is boring. But we didn't tell the editor before we submit. This is abelian statistics. And then if you could manage to create lattice defects, you can do non-abelian statistics. And that's the follow-up work, which unfortunately I would not talk about. So I'm here to talk about this work. It got posted on arXiv a few weeks ago. Is on lattice gauge model. So I guess, well, here's the idea. Again, it comes to this Kitaev model, and we are talking about Kitaev, well, at the limit that, okay, a certain limit, it shrinks down to Kitaev model, but the Kitaev model being a Z2 lattice gauge model, and this is another extended version of it, that you have matter, you have your group of qubits, you call them matter qubit, and you call them gauge qubit, or the qubits that are sitting on the link queue connecting the matter qubits. Both symbols meant to just show you qubits. I just give them names to realize essentially the dynamics under this lattice gauge model. Well, what we do, instead of just going for this directly, we take advantage of the fact that this is a lattice gauge model, meaning that the, let's say, Gauss's law is incorporated in it with local symmetries, and you can use that to kind of take out the gauge degree of freedom, and you come arrive at this Hamiltonian, which is maybe more familiar to you. It's just the Kitaev model, and there is HM and HE terms. And then there's a nice interpretation to the clock violation and the vortex violation as the existence of a charge and whatnot. So if the matter there was electric charge on a circular qubit, on a matter qubit, it would show up now in the absence of having the matter qubits in the link qubits that were surrounding that vortex, and it would show you in the magnetic flux that were going around the plaquette. So the matter's degrees of freedom have been integrated out, have been taken out by taking advantage of the GV, the local symmetry of the model. Okay, so that's what we want to study. For this study, since the great time of Edward Fradkin 1979 paper, we know the phase diagram of this model. Okay, it's not the ground state of this model is well understood, and as a function of this HM and HE that are intuitive names given to these parameters, is you see a deconfined phase and there is a confined phase. Close to the Kitaev, the origin, the HM equals HE equals to 0 is the Kitaev point. It's exactly solvable, and that would be the confined phase, meaning if you get the excitations, create excitations, they would freely roam around and they don't talk to each other, they don't do much. But if you change the HE substantially away from 0 or HM, you get to the confined phase. In the confined phase, you can imagine there is a string. Well, for now you can imagine, but I will show you direct measurement of the string that connecting the excitations together. Okay, and again, the ground state is well understood, and we come up, we come up with an ansatz to arrive at the well. Okay, the ground state is not exactly solvable, but it's still manageable. So you can come up with parameterize the protocol I showed you for the Kitaev point. There is an adjustable parameter theta, which allows you for any value of HM and HE that you like, non-zero values now. You can get very close to ground state. It's an ansatz, it's not exact ground state, but you can see that deviation from ground state is substantially small, that you can practically be at a very low energy state, very close to ground state of the system. Yes?
What is the most direct observable that tells you whether you are confined or deconfined?
I'll show you. You have to say it again. So, okay, good. Okay. For now, I want to synthesize the ground state of this model. I have not got to the dynamic yet. For now, we look at this, either you're smart or you collaborate with someone smart, we do the latter, and they tell you the recipe how to make the ground state of this model. Now, I want to show you excitation in this model, and now I would just go for Trotter step to show what happens in this Hamiltonian. So the first indication of the confinement is that after you create the ground state of this, you apply pi pulses and you create two excitations, and you just watch them as the clock of the AV violation, of the vortex violation, and then because we are interpreting as the existence of a pair of charge, and say where they are. As you can see, for two values of HM, the confinement parameter, when you look at it at the limit of HM large, you can kind of find the excitations where they were as you go down and look down in time. But then when the HM become close to zero in the deconfined phase, you can see it is kind of going all over the place. Okay, that as is showing that the color of the red getting washed out. Okay, well, you think about it, these particles are kind of wiggle in their place, and this initial state is not the best choice, because down to quantum fluctuations and whatnot, they are moving and whatnot. Did they move themselves? Were they closed by string? This was not the best choice of initial state. You can get slightly clever, more clever, I don't know. And you can create a slightly better initial states. The motivation or the thinking behind it is that you have Earth and Moon going around each other, and if they're connected by a string or whatnot, their motion would be very much affected. So you give it angular momentum, kind of. You want to give it angular momentum to your initial particles, and that's what this initial state is about. Is the superposition of two ones created, and then you can, when you look at the separation of them, the fact that they are confined or not confined comes up very much more visually more attractive way, right? If they are confined, when that's the case of HM equals to 2, you can see their separation is not changing. When they take a snapshot of it, let me show you a snapshot of it. When you find one particle, you know exactly where the other one is with a very good probability. But in the case that they are deconfined, they fly apart from each other as if gravitational field between Earth and Moon has turned off.
Earth and Moon, they are only confined if the energy is, beyond the threshold as a negative. So is it a question of energy actually?
A question of HM.
Well, but HM is a parameter, and say for Earth and Moon we have the gravitational attraction, and then it still depends on the energy whether you are in a bound state.
Yeah, don't read too much into this analogy. We have this phase diagram in here, which tells us HM, forgot, maybe about 0.6, they go through the phase transition.
Is it because the potential grows linearly in this?
Yes. That's the phase diagram, which is decades old, essentially. But maybe let me make it super clear. The phase diagram has been drawn and whatnot, is decades old, but the challenge is to create dynamic and observe them. That's where the theoretical values failed, are challenged, and that's where we are coming in. So we can see clear signatures of them going apart from each other if you manage to give them some initial state to give some momentum, some angular momentum to the initial state. All right, that's great. So I told you that there is also a string connecting them when you create two excitations. So what we are going to do, not to convolute the dynamics, we are going to create two excitations, move them apart to the end of the chip, end of the small group of qubits, and we take them out of the dynamics. So we are creating a string and stretching the string, and then, but we are pinning the particles to their place by taking them out of the trotter dynamics. And now we are going to look at this dynamics of the string, right? You're like a violin string. You're hoping that in the confined, very confined case, this is a stretched violin string, does not wiggle around much. And then when they are loosely connected, the confinement is weak, then you're thinking this string would just go up and down free. So the parameter which we chose to measure is the ZZ correlation, and it shows you this behavior that I just described with my hand. In the confinement case, HM equals 1.4, you can see that the string created is kind of frozen in time, and it doesn't move much, as it shows in this ZZ correlator. This is the third row in this spatial temporal maps that we are showing. And then in the top one, when there is no confinement, it's very difficult to define that what is not even to hoof the string is not defined, and this correlation show you kind of equal being in all over the places. Okay. So there is strings and they wiggle around, and the line cut. So I'm just trying to convince you this is not a cherry-picked one. So you can see that in time, and then in the lower panel you can see them in as what different qubits are doing in a space and time. So you get a very good picture of what's happening in here. So there are strings, and the strings could break. We can measure the breaking of the string connecting them. In this case, there could be a vacuum fluctuation leading to create a string from actually vacuum, or the string is there and then sometimes sometimes a pair of particles are created as a result of breaking the string. In these panels, we're trying to convince you that the probability of getting a pair of excitation on the top part is further increased because there was a string there. So we measure. Of course, there's a background to be removed because I want to show you that this string, the probability is not just coming from the coherence in the system, and I get this AV become non-zero by the coherence and whatnot. But what I want to show you is that after subtracting the background, you can see that the probability of having particles, excitations on the top part is substantially increased because there was a string there stretched there in the beginning. Okay, and the two end particles are fixed, but then the middle one, the string in the middle could break, and that could lead to formation of more probability of formation of particles in the top part of the same data. I'm showing you slightly differently. Slightly different. So we focus in two specific qubits. Highlighted qubit A1 and A2. And then there's a background going on. This is down to decoherence. The probability of getting excitation, of course, is increased. But then you can see that on the top one, where the position of qubit A1 is, then the probability of having a particle is substantially different than what is simply a background would suggest to you as a function of time. Okay, good news. I might even finish on time. Okay. This is first part. The second part, actually, the connecting theme is this notion of lattice gauge models, and this done in a different collaboration. Well, let me actually say something about the nature of collaborations and how we work. This works that I'm presenting you done by our student researchers that we call them residents. They are PhD students that come to our group for an extended period of time, for about a year. Their PhD advisors hate me, but they really love the deal. So if you want to know more, you can come and ask me. If they don't make a mess, it's going to appear on arXiv tonight. This is a story that probably closer to your heart, and it's a story of many-body localization in the absence of disorder. Okay, well, I messed up. Okay, I didn't know this was animated. I think you know this part better than me. In the absence of disorder in a wire, let's say, there is a blocks theorem tells you that there are extended wave functions and whatnot. And then came the Bell Lab and the semiconductor industry, and then the interest understanding what the role of defect is in wires and semiconductors. And then came the absence of diffusion in certain spin models, 1958, Anderson. And then we thought, okay, sure. In the absence of interaction, there would be localization in 1D system, let's say. But then we say, we are good. If there is interaction, we are fine. This worldview shattered in 2004 or 6 by paper by Pascual-Leiner and Altshuler, which they said that, well, even absence of disorder, even interaction could not help restoring the conduction, and you might get localization even in interacting systems. But these two big Anderson localization is a non-interacting physics and has been seen in sound waves and many other places. And kind of the notion of localization is very much synonymous in our minds with disorder. Can we see localization in the absence of disorder? This has been a theme maybe since a decade ago. We are not the first one talking about it. There are lots of theoretical ideas that has been proposed of how to realize localization in a many-body system in the absence of disorder. But we are the first one, we took it to 2D. So consider a Hamiltonian. Let me show you the surprise, and then when I describe the physics, is extremely maybe boring. Again, it's tightly connected to lattice gauge models. If you know the physics, you know that's where it comes from, because that's where you have lots of local integrals of motion and a chance for kind of constraining the dynamics or localization. Anyways, but this is the physics aside. There is a model. I just want to show you that there is no disorder in it. All the terms that you see are outside the summation, so no term has disorder in it. And then I consider two initial states. They're a little complicated. Let me walk you through it. But they are also translationally invariant. This is a periodic boundary condition on 38 qubit I'm about to show you. We are considering two initial states that they are both translationally invariant, and there is a hump in the energy. There's a 1 qubit almost flip in the middle of it. So for just reasons become obvious in a second, I call them gauge qubit and matter qubits. And all the gauge matter qubits are on X or Z. All the gauge qubits are tilted, except one in the middle of the gauge qubit, which is tilted different than everybody else. So you put that aside, the initial state is translationally invariant. Initial state does not break translational invariance. The Hamiltonian doesn't. Yet when you look at the dynamics, you see a very two distinct behavior in these two cases. So I'm showing you what the various terms of the Hamiltonian doing. If we give them name because, again, coming from a gauge model. So when you look at it, you can measure the gauge polarization. You can measure which in the lower part, I'm showing you what term in the Hamiltonian it is. And the last column is the summation of all the terms in the Hamiltonian. So one lower row, you can see kind of frozen in time, then nothing changes as if everything is localized. And the top one, you see a very vivid dynamics of oscillations and whatnot, and indicating that it's going to thermalize because there is a propagation. This disturbance has been propagating through this closed 1D wire. Okay, so this is the evidence, and this is the physics behind it. How do you synthesize something which shows you this localization in the absence of disorder? So we got to disguise the disorder, and this is the recipe for it. Let's say you have qubits on the link of a square lattice, and this is the disorder Hamiltonian you want to study. This is the disorder term. Let's say someone asks you to study this where this disorder term is a binary disorder. What you could do, you can introduce a group of ancillary qubits, and then instead of having a parameter, you can introduce this Pauli operator in the Hamiltonian and take it out. But since this operator commutes with the Hamiltonian, it's going to be a constant of motion. So de facto is going to act as a disorder while your Hamiltonian is not disorder. Right, look at it now, this one. So if you don't need to be very clever for this part. You just don't need to choose weird initial states. If you just choose a product initial states, now the eigenstates, the initial states also respect this construction that I'm suggesting. You arrive at something like this. You have initial states, which can be effectively written as this tensor product of these two parts. And then the choices that you make for your matter qubits, for your ancilla qubit, effectively act as disorder for your potential. So if you chose these sigma x's, for instance, to be all the same, you get a disorder-free. You would be confined to a disorder-free sector of this Hamiltonian. And if you choose different values, then you would be in different sectors. But the beauty of this is that now you can be in the superposition of all these sectors. And the superposition of all these sectors would be disorder-free. So each sector in this, I don't know what this is a schematic all of us draw and none of us know. It's like a matrix, let's say, Hamiltonian in some representation. It's made of sectors now, decoupled sectors. Each of them is set by these gauge degrees of freedom, what you chose for them initially to be. But if you chose these degrees of freedom to be, let's say, along Z, where the degree of freedom, where the gauge is sigma x, then you are in the superposition of all sectors, which is again disorder-free. So in the lower part of that matrix, I'm showing you how that disorder-free came in the example I showed to you. So the dynamic would respect this segregation that has been made, and it look all good so you can be in the superposition of all disorder sectors without seeing the disorder, and that's where the localized behavior was coming from. Because when you're thinking about them as binary choices that you make, for most cases they're disorder. Therefore, the dynamic was localized. But
Sorry, Pedro, can I ask a question?
Sure.
I mean, so you're choosing some particular initial state, so it's a particular superposition of all these different sectors. Isn't that disorder?
So the making disorder free was you have to be clever. Usually you're in the superposition of many disorders. Well, let's just go. So let's just look at this example, like sigma x. If I choose sigma x for all qubits, then I'm in a particular sector. If I put sigma z in all qubits, every qubit is a spin up, then I'm in the superposition of all sectors. That's what we did. Yeah. Okay. Igor would kill me if I don't tell you this, so I tell it. This is a significant thing, beyond its gauge games that we play. And the significance of this problem is this: when you can be with one flip in the superposition of all disorder realization, that's an extremely effective way of sampling. When you're thinking about conduction in a wire or so, it could be very much affected by rare events. So when you're doing a numerical simulation of a, he would kill, right? Okay. When you're thinking about numerical simulation, you have to do lots of disorder realization, and yet you may not. There might be rare events which would affect transport in a real wire because it's very long, versus numerical simulation, which you may not ever get there. So local linear observable that are local in density matrix at least can be very effectively sampled this way, and in this sense, I think is a very key feature to pay attention to. I just want to finish by saying that we could take this to 2D. This is the last bit of data I showed, so I'm a good citizen. But of course, for us, it's not very challenging to get it to 2D. And what you see is what maybe you expect, that when you create an excitation, energy excitation on top qubit, in the case that you are in a single disorder sector, this excitation gets fade out and goes kind of all over the system. But in the case that I managed to be on the superposition of all disorder sectors, although on some it's disorder-free, but effectively act as effectively look like a disorder system, and the pattern seems to be frozen in time. Do not worry, because I will show you a cut through it of what happens. I would not hide things behind a movie. So this is to maybe communicate the pain that our colleagues took to do the Trotter step dynamic over this Hamiltonian. It was not very simple, but you can see the red curve is the top qubit, which is really going up and down, exchanging energy with its surrounding qubits, but the other qubits are very coming down. So before a tourist ask me, can you take it to the thermodynamic limit and see what happens? The answer is, of course, not easy for us to answer that question. But you can see at least maybe the claim we can make is we see clear signatures of breakdown of ergodicity, at least for short time scales. Okay, this is entanglement measurement, but we're not going to get there. Well, okay, this is the work that infrastructure that Google team has put together gives you. So this is not really work of a small group of people, and this is the team of Google. But more importantly, we have been benefited from collaborating with many academics across the globe, and we are very thankful for them to be with us in this journey. Thank you.
Thanks for the talk.
Sure.
I had a couple of questions about the first part of the talk.
Sure.
So in the first confinement, deconfinement dynamic stuff, first question is, what role do the JM and JA terms play? Because it seems most of the confinement stuff was just done by the HM term. And the second question is, in the confined phase, when you have these sort of two charges bound together, do you expect the bound charges to delocalize, like even though they're bound, but they can themselves delocalize? So do you see?
So one question at a time. I think the physics is much better understood. Let me just show you the phase diagram. The physics is understood when one of the HM or HEs are zero. So we were very careful. I'm showing you cut through HM, but HE was always fixed to a non-zero value. Otherwise, we would not be impressing anybody. So for us, of course, it's very easy to get HE to be non-zero and then go dynamics and change HM if we want. So that's my thing that I want to. I maybe didn't mention, but it was always HE was zero when I was showing HM values.
GE and JM don't.
Oh, sorry. Yeah. Okay. Then another question. Yeah, that was just to show you JM and JE were set to zero because I want to give the meaning to the axis of time. The time is in the unit of 1 over JE or JM, which is 1. So this time is, of course, a Trotter step, but it would be pointless to show a step. But this JE is in the unit of 1 over JE.
I meant like, do those terms play any role in the dynamics? Like the project start, if this state did play any role in the dynamics? So would I see the same physics if I just had the HM and HE?
Oh, if you have HM and HE, you have non-interacting bunch of independent nothing. This is single particle. Sorry.
It's nice to see that this disorder-free localization is still alive after 10 years that we invented it. But I think in contrast to the standard MBL that is robust with respect to changes in the Hamiltonian, this is not, do you agree? I mean, this exists because you have these ancillary qubits that are conserved and commute with the Hamiltonian. If you change the Hamiltonian slightly and give them dynamics, it disappears eventually. That's what my understanding at the time.
No, there was an initial model that was written by people that actually we collaborated. I think that model was, unstable. But I don't think, I think it's, is as good as it gets for like any other Hamiltonian. You can perturb it. Well, would it survive in the thermodynamic limit and our system and all that? Is an open question, but it's not a fine tune. It's not a fine tune. It's not a fine tune Hamiltonian.
I think it is, yes.
No, I don't. You can add perturbation and you
No,
see.
but if you give dynamics to your select, you get, I think, the thermodynamic limit is phase disappear. At least that's what I believe and what other people believe, and I thought in particular ego would believe, but
Well, look, let's talk after. Yeah.
Okay, while we take the final question, maybe you can start attaching.
Now I have to claim I know my slides.
I guess maybe it's a little bit, I'm not sure, maybe I'm I'm just wondering why you call the many-body localization, because my understanding is, it's more like, for me, it's more like you have some symmetry constraints. This is more like a Hamiltonian fragmentation.
But because I see signatures of ergodicity breakdown.
Yes, and there are many types of case that ergodicity can break, right? I'm just wondering why you choose to call the many-body localization instead of, let's say, some like fragmentation of the Hilbert space, something like that. Because
No, there are two. There are two.
part of the Hilbert space.
Yeah, that was the underlying mechanism, and there's no disorder in it.
Yes.
And then ergodicity breaks.
Yes.
So ergodicity breakdown in the absence of disorder.